Welcome to Breeze Physics. I know sometimes it can feel like a whirlwind, but today we're going to make it a breeze. We are tackling the 2025 AP Free Response Question 1 involving a cart, a mass, and well, it's a momentum question. So let's dive in. A student has a cart of mass mc and a block of mass 1/5 mc as shown in figure 1. At time t equals 0, so we're right here, the cart is moving to the right across a horizontal surface with a constant speed vc. So they told us it's moving directly to the right with a speed vc, so they really kind of gave us a velocity there. And the student releases the block from rest, so the block is right here, and it is being released from rest. At t equals t1, the block collides. When it collides, it sticks on top. We now have something that acts as one big mass instead of two smaller masses. At time equals t2, the block cart system continues to the right with a velocity vf. So they gave us an initial condition and a final condition. All right, so let's read what the question is. On the axis shown in figure 2, sketch a graph of the magnitude px of the x component of the momentum of the block cart system as a function of time from t equals 0 until t is greater than t2. In other words, from the very, very beginning until the very, very end and beyond. How does the momentum change? Oh man, you're freaking out. You don't know what momentum is. That's okay. You actually need to know very little physics in order to solve questions like this. So let's go ahead and pull out our reference table. What I'm going to do now is I'm just going to look for the word momentum in my reference table. All right, I have found it. I have identified that a small p is the symbol for momentum, and I'm going to go find the equations that involve momentum. I see 1, 2, 3, 4 equations that involve momentum. That doesn't mean we're going to use all of them, but we're still just going to take them and we're going to write them all down. Let's jump back to the problem. So our first equation is that momentum is equal to mass times velocity. This just tells us that when a mass is moving, it has momentum. That's really all it's telling us. So that's what momentum is. It's okay if you don't understand that, as long as you can do the math. All right, our next equation tells us that when a net force acts on an object, it changes that object's momentum. When a net force acts on an object, it changes that object's velocity. When a net force acts on an object, it causes that object to have an acceleration. You will also notice that all of these have little arrows on top of them. The reason they have little arrows on top of them is because they are vectors. Real quick, again, a vector is a component with both a magnitude and a direction. It has to have a how much and a which way. The which way is very important. The fact that it is a vector is very important. Next, we are told that J, which is impulse, is when a force acts on an object for some amount of time. An impulse changes an object's momentum. So what do we see here multiple times that you might have noticed? That a force acting on an object changes an object's momentum. All right, last equation that we see has to do with the center of mass. Since this is meant to be a shorter video, if you understand it, basically if you have no net force and you're not changing the momentum of the system, the center of mass of the system is going to move with a constant velocity. So if you add up all of the momentums and you divide them by all of the masses, that velocity of the entire system will remain the same. If you don't understand it, don't worry about it, because we really don't need that in order to solve this problem. So let's go back to what we do need. We determined that if there is a net force, we change an object's momentum, and we are trying to graph this object's momentum with time. So we pick some starting point. Doesn't matter. Just pick a starting point. This is where we're going to start our momentum. Now we just need to see if we change the momentum with time. This entire system, if we were to look at all the forces on the system, do you see anything pushing or pulling that system? No. What are the only forces on that system? The only forces on that system are the force of gravity down on these objects and the force from the surface back up on those objects. Those forces act purely in the y direction. This question is asking us about the x direction. So there are no forces in the x direction at all. If there are no forces in the x direction at all, that means our change in momentum must be 0. Because if F net is 0, we cannot be changing momentum. Therefore, the answer to this question is a horizontal line. The momentum does not change. Boom! That was a breeze. Let's move on. The next question is asking us to derive an expression for the speed of the block cart system after time equals t2. So at the very, very end, what is the total speed in terms of mc, the mass of the cart, vc, the velocity of the cart in the beginning, and physical constants as appropriate. Begin your derivation by writing the fundamental physics principle or equation from the reference information. Okay, so let's do it. I've gone ahead and just put our figure back here. Remember, in the very beginning, they told us the velocity was vc of the cart. And at the very end, the velocity of the entire system was vf. And we also know that we have some important equations. Momentum is mass times velocity. That if there is a net force, we change momentum. And the important thing here is we know we are not changing momentum because the F net was 0. So let's go ahead and get rid of that. So in other words, the momentum in the beginning must equal the momentum in the end. Conservation of momentum, conservation of energy, of momentum, of mass. These are really important concepts. So all we have to do is take the very beginning, equate it to the very end, and we are going to be able to solve this problem really easily. So what I'm going to do here is I'm just going to say the momentum total at time t0 is going to equal the momentum total at time t2. And now we're going to solve this problem. So we're going to add up all the momentum in the beginning, all the momentum in the end. In order to do that, we need to remember some of our constants. So the mass of the cart is mc. The mass of the block is 1/5 mc. The velocity of the cart in the beginning is vc. The velocity final of the entire thing is vf. So, and the velocity of the block at the very beginning is 0. So all we have to do is put in everything. So we're going to say the momentum of the cart plus the momentum of the block in the beginning is equal to the momentum of the block cart system. Remember, they're one mass now, so I'm just going to treat them as one mass. Momentum is mass times velocity. So the mass of the cart times the velocity of the cart plus the mass of the block times 0, because it had no velocity, is equal to the mass of the cart plus the mass of the block times the final velocity. Now we're going to plug in the things that we know. We know that the mass of the cart is mc, the velocity of the cart is vc. We know that anything times 0 equals 0. We know that the mass of the cart is mc, and the mass of the block is 1/5 mc, and we know that the final velocity is vf. This leaves us with mc vc is equal to 6/5 mc vf. Hey, look at that. We are just going to go ahead and cancel mc because it's on both sides. And now we have that the final velocity times 6/5 is the initial velocity. Now to rearrange that, we are just going to go ahead and say, huzzah! 5/6 of the initial velocity is the final velocity. And that is our answer. Boom! That was a breeze. Let's move on. Okay, so I saved right here what our final velocity was in terms of our initial velocity, and it makes sense that it's less because if our momentum stays the same, if our mass increases, our velocity must decrease. If our velocity had increased, if our mass had decreased, our velocity would have had to increase in order to maintain that no change in momentum. And I saved our mass of the block cart system. All right, derive an expression for the change in kinetic energy, delta K of the block cart system from t equals 0 to t equals 2 in terms of blah, 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 all our constants. Same thing. We're freaking out. We don't know what we're doing. We go to the reference table. When we go to the reference table, we write down our equations. If you put your pen to paper, you will get answers. We see one equation that says K is equal to 1/2 mv squared. We see another equation that says the change in kinetic energy is equal to the sum of all the work done, which is equal to the sum of the forces acting parallel times the distance that those forces act. And then you're saying to yourself, aha, there were no forces. We said there were no net forces, so there's no work, so the kinetic energy doesn't change. Wrong. Kinetic energy definitely changes. Think about this. This block landed on the cart. If there had been no friction in the system, the block would have slid right off the cart. Instead, the block was accelerated forward because of a force of friction, and the cart was slowed down because of a force of friction. So there was a change in kinetic energy. Do we know the forces of friction? No. On the system, those sources of friction cancel out, so the net force is 0. But individually on that block and on that cart, the kinetic energies changed, and so we do have a total change of kinetic energy because there is a change internal to the system. So we don't know the forces, so we have to go back to this K equation. What does delta mean? Delta means change, right? So if we want to change, all we have to do is we have to say what was the final kinetic energy, what was the initial kinetic energy, and that will tell us the change. So we're just going to plug in these values of masses and velocities, and it's a simple plug and chug problem. So the change in kinetic energy is, in the final condition, the kinetic energy of the block cart minus the kinetic energy of the block plus the kinetic energy of the cart in the beginning. And I'm sorry, this is AP Physics, so that should be a little not. All we have to do now is plug in. The change in kinetic energy is going to be equal to 1/2 mass block cart velocity block cart minus 1/2 mass block velocity, don't forget the squared, velocity block squared plus 1/2 mass cart velocity cart squared. And we're just going to plug in to solve. You know, this is starting to look like a lot, but stick with me. Delta K is equal to 1/2. The mass of the block cart is 6/5 the mass of the cart. The velocity of the block cart is 5/6 the velocity of the cart minus 1/2 the mass of the block times 0 squared. The mass of the block started with 0 velocity plus 1/2 the mass of the cart, the velocity of the cart squared. All right, so it's getting a little easier. This is 0. This goes away totally. So now we have that delta K is equal to 1/2. All right, the first 6/5 and 5/6 cancel, so we are left with just a 5/6. 5/6 mass of the cart, velocity of the cart squared minus 1/2 mass of the cart, velocity of the cart squared. We are getting there, I promise. Delta K is equal to 5/12 mass of the cart, velocity of the cart squared minus, I'm going to write this as 6/12 instead of 1/2 mass of the cart, velocity of the cart squared. Wow, we are so close. What do we end up with? The change in kinetic energy is negative 1/12 mass of the cart, velocity of the cart squared. If you could follow along with just plugging in those variables, plug and chug, then boom, it's a breeze. Let's move on. Final question. They ask us about dropping a brand new block on top as that cart is moving. So that block falls, it drops on top. When it drops on top, it does slide. It slides this way relative to the cart. There is some friction on it, just like we talked about earlier. So there's some friction on it this way. There must be some friction on this in this direction, because there have to be equal and opposite forces. And they ask us how the change in momentum, or what the change in momentum is. Does the momentum increase? Does it decrease? Does it remain constant? And remember, this is really the same as the very beginning. We draw a box around this entire system. Around this entire system, those two forces cancel each other out. There are no forces that are acting from outside this system, and therefore, if there are no net forces acting from outside that system, then there can be no change in momentum and it must remain constant. So all you're going to say is no external Net force, no change in momentum. F net equals delta P over delta T, and then you can just say 0 and 0, and you are good. Boom, that's the entire free response question 1. That was a breeze. Until next time. Hey, I just dropped the walkthrough for the 2025 AP Physics free response question 1, and I was so focused on the physics, I forgot to say if you liked the video and if it helped you out, please like and subscribe. You can also check out my website where I'll post helpful notes. You can request future videos, and you can even request virtual tutoring. Until next time, keep it breezy.